Welcome learners in the series of videos on topology. We are looking at separation properties. Now in this video, let me state a theorem that every regular second countable space is normal, and then we will talk about the statements of Urysohns Lemma and the stasis extension theorem. So let me first state the theorem. To try to prove this theorem, every regular second countable space, every regular second countable space is normal. So every regular second countable space is normal. Okay, so space X is regular. It is second countable, means it has a countable basis. So using these two facts, show that this X is normal. Okay, so I will leave this as exercise. One can try to prove this, that every regular second countable space is normal. So as I said, let us just state the Urysohns lemma and the extension theorem. So we'll just state it. We are not going to prove it. So first you have Urysohns SOHN, URYSOHN, right? Urysohns lemma. I will just state it as I said. So let X be a normal space, X be a normal space, and let A and B be disjoint closed subsets of X. Subsets of X. That means we have a normal space and we have two closed sets A and B whose intersection is empty. Okay, let closed interval A comma B be a closed interval in R. Okay, so this A comma B is a closed interval in R. Then this lemma says then there exists a continuous function that is map, say f, from your space X to A comma B such that f at X will be equals to A for all X belonging to a set A in A, and f at X is equals to B for all X belonging to B. Okay, so of course this is a function from X, and we know that A and disjoint closed subsets of X. I guess I missed something. It should be union of these two has to be whole of X, right? So here there is nothing special about this A and B. You can take the interval from 0 to 1. Okay, close interval 0 1, and precisely what it says is any two disjoint closed sets can be separated by a continuous function. This is a continuous function. Okay, that means you have a topological space. We just go here. You have topological space. We have two disjoint closed sets here. It says there exists a continuous function for which, when you take all the elements from here, let's say A will be mapped to the small a, or maybe you can say 0 1 if you take, so 0, and if you take this B, then all the elements from this B will be mapped to B. In fact, this is if statement, but let's take this version of this. Okay, so I'm just stating it. Let's move ahead and state extension theorem. I'm just stating it. Proof of this can be done in the another course. That is Tietze. Don't know how to pronounce it. Please excuse me. Tietze. Tietze extension theorem. Extension theorem. I'm stating this from the standard book by James Bunkers. Okay. So let me state this, that X be a normal space, be a normal space, and let A be a closed subspace of X. Okay, so we have a normal space and we have a closed subspace A of X. Then there are two statements. In fact, we can make a generalized one. Any continuous function or continuous map of A into a closed interval, into a closed interval, say A comma B of R, real line of R, may be extended to a continuous map on X into 0, 1. Let me not write 0, 1, let me write A comma B, because I have taken A comma B. Again, there is nothing special about this A comma B, you can take 0, 1. Okay, that means if we have a map F from A to 0, 1, you can extend it to a map from full space to full space X to 0, 1, which is a continuous extension. Okay, let me write the second statement as well. Any continuous map the map of A into R may be extended to a continuous map of all of X into R. That means, let me just tell you roughly, if we have a function f from say closed interval A, closed subspace A to say A comma B, then which is a continuous function, we can have another function f bar from full space to A comma B, such that f bar restricted to A will be equals to f. This is a slight variation of it. So we are not going to prove this. We may prove this in the next coming videos if possible. But this is all we are supposed to do in the first course on topology. So we have studied all the basic concepts. We have studied the connected spaces. We have studied compact spaces. We have also seen the countability and separation axioms. Okay. Now in all these videos, I have proved many statements. If you have any statement, any proof which can be simpler, which can be made simpler, you can contact me. If you have any doubt, you can contact me on this email ID. Let me put my email ID here. maheshgawk at the rate gmail.com, or you can yeah, you can put me a message on you can put me an email on this email ID. If I can help you, I will be happy to help you. So I hope you have learned many things in this series of videos on topology. So thank you very much for watching these videos and putting your queries through emails and phones. So see you in the next course in the coming time. Stay safe, stay home.